Welcome to the unit on cellular energy. In this unit, we will be discussing how cells are able to harness energy from their environment and convert it into a form that allows them to do the work necessary to support life. There are three main topics in this unit: the laws of thermodynamics and energy conversions, an introduction to metabolism, and the role of enzymes in chemical reactions. In this video, we'll begin with the laws of thermodynamics. Energy is defined as the capacity to do work, and all cells require energy to sustain life. There are many sources of energy on this planet, including sunlight, electric, and chemical energy in the food we eat. However, although there are many different energy sources, there are only two main forms of energy. Energy is classified as either kinetic energy or potential energy. Kinetic energy is the energy of motion, such as this ball rolling down the stairs, or a muscle contracting when you make a fist. Other forms of kinetic energy include light, due to the movement of photons or light waves, electric, due to the movement of electrons, and thermal energy, due to the movement of molecules. The higher the temperature, the faster the molecules in a system move. Potential energy is energy not associated with movement, but rather is stored energy. Potential energy depends on the structure of the object or its position within its surroundings, and this energy is released when there is a change in the object's structure or position. For example, when the ball is at the top of the stairs, it has high potential energy because of its position due to gravity. Another example of potential energy is chemical energy stored in covalent bonds, such as those shown in this starch molecule. Energy can be converted from one form to another. As the ball begins to roll down the stairs, the potential energy is converted to the kinetic energy of motion. When the ball reaches the bottom of the stairs, its remaining energy is stored as potential energy. But since some was converted to kinetic energy, the ball now has a low level of potential energy. This conversion from one type of energy to another is described by the first law of thermodynamics. This physics law, also called the law of conservation, because it states that the energy is neither created nor destroyed. It simply changes from one form to another. In this figure, we see four boxes of energy on the left. After the energy transformation, we still have the same amount of energy in four boxes. However, they have been transformed to another shape. Earlier, when the ball was at the top of the stairs, it had a certain value of potential energy. When the ball rolled down the stairs, much of the potential energy was transformed into kinetic energy, but the total amount of energy remained constant. When energy changes form, the total amount of energy remains constant, but the amount of energy still available to do work will decrease. Therefore, there's a price you pay in the loss of energy to do work when transforming energy. This is described by the second law of thermodynamics, which states that the universe is always moving towards an increase in entropy. This is the amount of disorder in a system. The lost energy available to do work is heat energy. Heat causes molecules to move faster, which increases the disorder of those molecules, leading to an increase in entropy of the system. You can see in this figure 4 boxes of energy are still present on the left and right sides of the arrow. However, one box of energy is released as heat and is no longer available in the cell to do work. The release of heat is key to how living cells fit within the second law of thermodynamics. A cell is a very organized structure. Thus, it would seem to be against this law of increasing disorder. However, for every reaction in the cell, a small amount of heat is released. In this reaction, the cell is doing translation. It is taking amino acids, represented by the green circles, and converting them into proteins. By covalently attaching the amino acids together to form a protein, this is increasing the order of the cell, because the individual amino acids are no longer free to move around separately. In order to maintain this order, entropy or disorder must increase elsewhere. This is accomplished by the heat the cell releases. When a cell dies, it no longer produces heat, thus it will eventually decompose as it moves towards a state of increasing disorder. Many energy conversions inside living cells involve chemical reactions. During a chemical reaction, the atoms keep their identity, but the bonds linking them change. For example, here, carbon dioxide and water react to form carbonic acid by rearranging the bonds as shown. Each chemical bond that is broken releases a certain amount of stored potential energy, and each chemical bond made requires a certain amount of energy to form. In a chemical reaction, the molecules on the left of the arrow are called the reactants or substrates. And the molecules on the right are the products. This reaction also illustrates why carbon dioxide increases in the atmosphere. Aqueous environments like the ocean are becoming more acidic due to the formation of this carbonic acid. Because each chemical reaction involves making and breaking bonds, which uses or releases energy respectively, we can determine how much overall energy will be produced by a chemical reaction, if more energy is released than required, or we can calculate how much energy is required by a chemical reaction if more energy is needed to form bonds than is released. The amount of energy in a system that is available to do work is called the Gibbs free energy. Every molecule has a set amount of Gibbs free energy based on its atomic makeup and chemical bonds. You can calculate the changes in free energy as a reaction moves from the reactants to the products. This is designated as delta G. Going back to the chemical reaction of carbon dioxide and water, generating carbonic acid, we can calculate the delta G for this reaction. Carbon dioxide has a free energy value of 94.26 kilocalories per mole, and water has a delta G value of 56.68 kilocalories per mole. The free energy in carbonic acid is 148.92 kilocalories per mole. The equation for calculation the change in free energy is the delta G of the products minus the delta G of the reactants. So for this chemical equation, be 148.92 minus the sum of the free energies of the reactants which is equivalent to negative 2.02 kilocalories per mole. A negative sign means that energy was released from the system because there was more energy present in the reactants than in the products. This energy must be released because energy cannot be lost based on the first law of thermodynamics. The Gibbs free energy of chemical reactions can be depicted in graphical form, where the amount of energy is on the y-axis and the chemical reaction is on the x-axis, moving from reactants to products. In our calculated example, the reactants had 151 kcals per mole of energy, and our products had 148 kcals per mole of energy. So our graph goes from a higher amount of energy to a lower amount of energy as we moved through the course of the reaction from the reactants to the products. This difference in energy is the delta G of the chemical reaction. In this example, we have released energy to the system, resulting in a negative delta G. This is called an exergonic reaction exergonic reactions will occur spontaneously because they release their energy, which allows them to fit within the second law of thermodynamics. Other reactions, called endergonic reactions, require energy to be put into the system because the products contain more energy than the reactants. These chemical reactions have a positive delta G and are non-spontaneous. They cannot occur on their own. If chemical reactions with positive delta Gs are non-spontaneous, how do these reactions occur in a cell? In this example, we have one chemical reaction where reactant A is converted to reactant B. In order to occur, this reaction needs 10 kcals per mole of energy put into the system. This energy will often come from a second spontaneous chemical reaction in a process called energetic coupling. So if we have a second chemical reaction where molecule B is converted to C, producing 15 kilocalories of energy, then this released energy can be used to power the first reaction. There are some important requirements, however. One of the products of the first reaction must be a reactant in the second reaction so that the chemical reactions are tied together. In this example, A is converted to B, which is then converted to C. The other requirement is that the second reaction must produce enough energy to provide all the energy plus extra required for the first reaction. The sum of reactions 1 and 2 must produce an overall negative delta G. For this example, plus 10 kcals per mole plus negative 15 kcals per mole leaves us with an overall delta G of negative 5 kcals per mole. Thus, reaction 2 can be used to power reaction 1.